is like 8-bit bytes.
Power overwhelming.
Yeah, using the power too.
Wait, sorry, does it assume that the numbers you get in are 8-bit bytes?
No, it's arbitrary.
Okay, I have no idea why I didn't put it on the syllabus, but there is new homework,
You define how many bits
in case you were wondering.
You haven't even finished the old homework.
I know.
Oh.
I wouldn't want there to be a gap.
Okay.
That's
Which one
do
do you
right
before break? After
Straight
break.
ahead.
Woo!
No problem.
So, this is the full-on Huffman compression program. And I have given you my header files, but you are not bound to use them at all. In fact, you'll notice that my header file is a little different from yours because I wrote two different bit streams, one for input bits and one for output bits. And the class that you wrote, it just merges that, the input and output, into a single class. So take this with a grain of salt. This is more guidance than anything else, just sort of one way of implementing Huffman compression. Let's go up here and have a look. I'm asking you to write a program called hzip that will read the file, will do the frequency count, will build the Huffman tree, will write the header to the compressed file. The header is information that will be used to decompress the file. It'll write the header, and then it will go through the original file byte by byte and encode it and put it out to the compressed file, and then you're done. And then an hunzip program, which will open a file that has been created by hzip. It'll read that header, it'll rebuild the Huffman tree, and it will then go through the input, the compressed file, bit by bit, and decompress, blow it up back into its original collection of bytes. Yes?
Does that mean we're going to have two different make files for this?
No, in fact, I'll show you a trick later. It's not really important that we learn it now, but you can actually use what's called a symbolic link in Unix, and you can check how the user called the program. If they called the program as hzip, then we'll do zipping, and if they called the program as hunzip, then we'll do unzipping. But I'll show you that trick next week sometime. What I want to do today is talk about array-based representation of trees, lists, so forth. Everything that we've done up to this point, you did do a little reading about it in Gishard's notes, but everything that we've done so far with linked lists has been using pointers. And this is kind of a step back from that, where all of our nodes are going to be in this pre-allocated array, and all you're going to be doing to build the list is just tweaking index values. And I'll talk more about that in a minute. Here's my Huffman class, and it turns out that all I need are 513 nodes in order to represent even the largest possible Huffman tree. And so rather than deal with the pain of dynamically allocating and deallocating nodes, what I'm going to do, since 513 is not that big of an array, I'm just going to use an array and not worry about dynamic memory allocation.
Is there a reason why 500?
Yeah, we'll talk about why it's 513. So there's all that. I don't remember if there's anything at the bottom. Yes. At the bottom, I describe what the header file in the compressed file looks like, what the header of the compressed file looks like. In other words, how do we write the Huffman tree out to the compressed file, and then so that we know how to read it back later. So at the bottom I describe that, but I'm going to talk more about it today and next week. Yeah, so I'll return to this later today or possibly Monday. Let's talk about. Can everybody see that okay? So I've got, this is a collection of huff nodes. Each column, starting with 0 and going out, is a huff node. And let's see what a huff node is. So a huff node has a left child, a right child, a parent, a wait, and a next. And I've got all 5 of those guys listed here in the huff node. I've got the wait, the next, the parent, left child, right child. I also have the byte and the node number. You can think of this as an array of huff nodes. So here's the first huff node, the second one, the third one, and so forth. And it's sort of like that statically allocated array that I had in my huff node class, except this is a much shorter one because I'm only going to be encoding things that have capital letters in them for this example. So it's a much shorter, simplified version of the full version. So what I would like to do is encode the word anaconda. And the first thing that you're going to do is a frequency count. So there are what, 3 A's? And there are 2 N's. Correct me if I make a mistake. There's 1 C. There's an O. And a D. Is that everything? ANACONDA. So that's what? 8 characters. And then 3, 4, 5, 6, 7, 8. Yes. So I've got. So that's. You can imagine doing that, right? You go through the file byte by byte, and if you get a byte, you increment a counter for that particular byte. So you do this frequency count. And then what you do is you want to sort these nodes by weight. And you want to do an ascending sort. Now, by default, what we'll do is we'll have this pointer that points at the beginning of the list. And I'm going to move this guy around as I go through this, this example. So by default, we're just going to say point at the first non-zero node. And by non-zero, the first node that has non-zero weight. So all these blank nodes have 0 weight because they didn't occur in the file. And I'm just going to point, I'm going to create a sorted linked list, and I'm going to start by pointing the list, the beginning of the list, at just the first non-zero node. And then what I do is I go to the next non-zero node, which is C, right? And I insert it into the sorted list. So this guy, since it's an ascending list, is going to be, and let me just put next here as -1. -1 is a signal, is the null pointer in this case. So I move to the first non-zero node, the next non-zero node, which is C, and I see that C belongs at the front of the list. So I take the head pointer and I move it to C, and I make next 0. Right? Then I move to the next non-zero node, D, and I see that D is less than or equal to C, so it belongs at the front of the list. So I'm going to move the head pointer to this guy, and I'm going to make next 2. And I keep going. The next non-zero node is N. N belongs where? So after D, right? It belongs after D?
After C.
I'm sorry, yes, after C. It belongs after C. So C is going to point at what? And so this will become 13, right? And then what's n going to point to? 0. Good. And notice the head pointer stays in the same place. So now you go to the next non-zero node, and where does it belong? At the head of the list. So we'll put that there, and we will make, where did I just come from? D?
3.
Thank you, 3. And so now I've sorted the list of nodes. It's helpful to think of each of these nodes at this stage as a tree, a trivial tree, a one-node tree. So we sort the nodes by weight in ascending order. Now we build the tree. We join the first 2 nodes under a new node. Now, the new nodes are all going to be placed out here. Right? Because all of the nodes below that line are representing characters.
So would this just be like a static array or just like jumble of nodes that haven't necessarily...
It's not a jumble of nodes. It is literally a static array.
Okay.
2n plus 1 in size? Or...
Yeah, we'll count. We'll be really careful about how to count, and you're going to see how to count as I go through this process. So you build the tree by joining the first 2 nodes under a new node. So we create a new node. The first new node is going to be here, and we join the first two nodes. So where is the first 2 nodes? So O is the first node, and then down here to D is the second node, right? So we're going to join those 2 guys under a new node. What's the weight of the new node? The weight of the new node is the sum of the 2 combined nodes. So in this case, the weight is 2. The first one will be the left child, so that'll be 14. And the second one will be the right child. What is that, 3? Yes. And what we'll do is, we're good there. Now we get rid of this guy, and we move it. We get rid of O, and we get rid of D, and we go to C. So we remove O and D from the list by moving the head pointer to after them. Yes?
Do we set the parent before we do that?
Yeah, I forgot the parent. Thank you. So let's go back here. Parent should be what? 26.
We want to remove it from the list, but we don't want to delete the nodes, right?
Right.
Okay.
So
this a 2D array, or is it an array of nodes?
it's a 1D array of nodes.
Okay. So then you can. Okay.
So now I can get rid of the first 2 nodes by just advancing the head pointer by 2 nodes, right? So we go from here to 3 and then from here to 2. So there's the new head pointer. I don't know why that disappeared. Okay, then we will remove. Good Lord. What's undo? Control Z? There we go. Oop. Whatever, you get the idea. Okay. I have no idea why. Left-handed people struggle. Where am I here? Sort the nodes, build the tree, join first 2 under new node. add weights. Remove the first two nodes. And we see how to do that simply by advancing the head pointer.
When you say removed, are you actually losing that?
I'm not losing them, I'm just removing them from the list, from the front of the list. And the way to do that is just to advance the pointer, the head pointer, 2.
Okay.
Now insert the new node into the list. So the new node is 2. You insert it into the sorted list. So where does it belong? Well, it definitely is bigger than C. It's bigger than D. And where do we go next? Sorry, C. Where? Oh, C goes to 13. Then 13 goes back to 3. Now we go to 2. Why is that 2?
13 goes to 0.
Thank you. 13 goes to 0. Very good. Okay, so it belongs after 13, right? Does everybody see that? So the new node out here belongs after 13. So 13, the next pointer becomes what?
26.
Yep.
Before we were ties, we were putting it in front, not behind. For example.
Oh, is that a tie? Yes, that's a tie. Good call.
Wait, does it matter?
It does. It doesn't matter, but computationally it matters. So hold on for a second. It's going to save computation.
Oh, okay.
Because there's no reason to go further once you've figured out where it belongs.
So our tree will be the same.
Functionally, it would be the same. So 2, just to be clear here, belongs before. Where was n going before? Damn it, 0. Thank you. Okay, this is much better meant for a computer, but so 2 goes after.
So we have to change 2's next. Yeah, 2's next should be 26. Well, that's.
No, because that's the thing. 26 goes before 13.
Yeah.
So it goes after 2.
Yes.
Okay, now we're good. So this becomes 26, right? And this becomes 13.
Yeah. Isn't it D that has 26 as a parent? Yeah. And not C. Yeah.
D has 20.
26 is a parent.
Yeah, where did I do it wrong?
It should be D that has 26 as a parent instead of C.
I'll take your word for it now.
Yeah, because our head pointer's at C. Yes. So that shouldn't be in the tree. Yeah. God, there's so many.
Okay. So I created a new node. I joined the first 2 nodes under that new node. I got rid of them, and I inserted the new node back into the list. Do it again. Join the smallest 2 nodes under a new node. So the smallest 2 nodes are here, C, and out there at 26. So 2 and 26 are the smallest 2 nodes, is that right? So the sum of those 2 guys is 3. And the left child will be 2. And the right child will be 26.
Isn't your choice of children a bit arbitrary?
It is, as long as you're consistent. Yeah. So I always just make the first of the 2 nodes that I'm joining, I make the first one the left child and the second one the right child. Yeah.
And that plays nicely with the whole, like, once you get a code, you can never extend it to another code concept.
It doesn't really matter because any code that's being generated by a tree is going to have the prefix property. That's generated by a binary tree. It's going to have the prefix property. So that's not as important. Mostly it's just for, your own health, mental well-being. The first one will be left. Second one will be right. But if you want to switch that, feel free. So we've joined two nodes under the new node, so we advance this guy 2 slots. So first we go to 26, and then we go to 13. So the head pointer is now here. Getting rid of that guy. And we insert the new node into the list. Oh, did I do parents? So 2 has parent 27. And 26 has parent 27. Okay. Now we insert the new node into the list. Where does it belong? Well, let's see. We start off at 2, then we go to 3. So it belongs after n, right? Or after 13. So n is going to point to 27. And this guy is going to point to where? 0. Still with me? Okay. Anything else left to fill in, or are we ready to go to the next 2 nodes? I think we're good. Okay, so now we start at 13 and 27. So we want to join those 2 nodes. 13 and 27 gives me 5 as the weight. The parent of 13 is 28. The parent of 27 is 28. The left child of 28 is 13. The right child of 28 is 27. Okay. Now we lop off the first 2 nodes. So we lop off 13 and we lop off 27. And that puts us down here at 0 for the head pointer. I must have forgotten to update the next pointer here at some point. So this should be a 28. Sorry about that. Does everybody see that?
So you want to resort before you log off?
Sorry?
So you want to resort before you log off the nodes?
No, after, yeah.
Okay.
So I move the head pointer ahead 2, and then I take the new node and I insert it into the list, into the correct location. And that next pointer on 0, I just forgot to update at some point. Looks like there's only 2 nodes left. Is that right?
Yep.
Yeah, I haven't been careful about this. This should be -1 to indicate that it's the end of the list. I haven't been doing that. Okay, so we now merge these 2 guys under a new node. So we have 8 here. Let's see. The parent of A is 29. The parent of 28 is 29. The left child of 29 is 0. The right child of 29 is 28. Is that right? This guy has no parent, so that should technically kind of be a -1 there. Next would be -1. And you would advance this pointer 2, and you would end up here, pointing at the root of the whole Huffman tree.
At this point, would we have to update 28's next? Because it seems like we wouldn't absolutely need to.
No, you wouldn't have to.
Okay.
Yeah.
'Cause
But let's do it anyway.
function of the next pointers is really only to make the list, right?
Yes, exactly. So I'll just leave it -1, whatever. that's the process that you're going to try to code. You're going to start out with, these are the leaf nodes here. And these are the new nodes, or the interior nodes. Now, if you start, how do you generate a code from this? So let's say you want the code for A. My outline kind of petered out here, I don't care. Watch the video. The code for A. So you start at A, and you go to the parent, which is 29, right? And you look back and you see where you came from. Is that possible? Right? So where did I come from? I came from the left child. Does everybody see that? I don't remember what we're calling zeros and ones. I'll say left is 1. So that gives me a 1. Now, lost my place. Parent 29, 1. And I guess we're done, aren't we? Yeah. So I know that I'm done with the code because the parent pointer is null. Let's do the code for C. So we start down here at C, and we see that the parent is 27. So we look at 27 and we see, where did we come from? We came from the left child. So that's a 1. Now we go to the parent of 27, which is 28, and we see where we came from, and that was a right child, so that's a 0. Now we go to the parent of 28, which is 29, and we see where we came from, and that was also a right child, that's 0. But that's not the code. I have to flip it. Right? Because what I want to tell you is how to get to the leaf, not how to get from the leaf to the root. I want to tell you how to get from the root to the leaf. So reverse and into file. Right, and that makes sense because if I start at the root node, here, 29, and I go 0, that's the right child. And then I go to 28 and go 0, that's the right child. And I go to 27 and I go 1, that's the left child. I'm down here at C. And I know that I'm in the right place because there are no children there. I know that that's a leaf because there are no children. And you can go on and do the rest, N and D and so forth. But that's the process. Okay, let's talk about the size. Worst case scenario for these 26 nodes. How much space do I need for new nodes? 25. I take away 2, I add 1. Take away 2, add 1, take away 2, add 1. 25? Does everybody see that? So worst case scenario, I need 25. Here we saw that we had 5 characters, and so we inserted 4 new nodes. Of course, this tree is only capable of handling bytes capital A through capital Z. We want to be able to handle all possible bytes. So let's talk about that a little bit. So there are 256 possible bytes. So that means we need an extra 255 for interior nodes. Okay, where does this get weird? Yeah. We imagine you are working through a compressed file. You rebuild the tree and then you start reading bits from the file one at a time. There's no way to know when to stop the decompression step. The only way to fix that is to introduce a fake character that we encode into every Huffman tree, and it occurs exactly once. So in fact, this fake character is going to be near the front of the tree, of the list. It won't necessarily be at the front of the list because any character that occurs once will end up getting inserted in front of it just because of the way we do our inserts, but it'll be near the front of the list.
So if you don't have that, will it just decompress everything and then sit there in a while loop trying to continue decompressing?
Yeah, there's just no clean way to stop it.
Okay.
Is essentially the problem.
And is that only because we can only print out invite units?
You know, kind of. So, yes, right. You can imagine when you compress one of these things that the compressed file will end up with a number of bits that is not divisible by 8. So that last byte buffer might have 3 significant bits in it, and then it gets dumped out to the file. The only way to get it, so you could say, oh, why don't we just let C++ handle finding the end of the file, right? So C++ is certainly not going to go past the last byte, and you can detect that, right? You can say, if you get past the last byte, we're done. There's nothing left. The problem is, let's say you've written 3 bits to that last byte buffer and you've actually flushed it. So there's 5 bits in there that are junk. So you're going to start reading those 5 bits and you're going to start working your way down the Huffman tree. And you may get to a leaf, you may not get to a leaf. Let's just say you're sitting at some interior node and then you suck in a new byte buffer. You've gone past the end of the file, so EOF becomes true, and you stop. And you've kind of done this extra traversal of junk. I guess the thing that you'd be worried about, not so much that you would end up at an interior node, what you'd be worried about is that you ended up at a leaf somehow based on the junk, and you threw an extra character into the decompressed file because you thought the junk was an actual character. And the only way to stop that is to encode a sequence of bits that tells you bip, 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 done. This is the end of the file, no matter how much is left in the byte buffer.
Okay. So we've talked about it like we're printing out 1s and 0s.
Mm-hmm.
Oh, but we're not. We're just printing out characters. Okay.
So we need an end of file code. So all possible bytes plus an end of file code means you need 257 leaves and 256 interior nodes. And that gives you the 513.
Why do you have to have it as a leaf and an interior node? Or, like, why does it add to both of those counts?
Well, we discussed earlier that if you have n leaves, you need n minus 1 interior nodes, right? So
Oh, because it's still a potential character. Oh, okay.
it's not a real character, but
Yeah.
so
Right.
so if I add 1 to here, then I've got to add 1 into over here. It's just, yeah. So the leaf node possibilities range from 0 up to 256. The values range from 0 to 256. And then the new nodes go from 257 up to 512. The interior nodes. All right. So you have this notion now of what it takes to build one of these guys. Let's talk about frequency counting. I don't know why I'm dyslexic about Q's and G's. Frequency counts. Let's sketch a frequency counter. So let's pretend that we have an input file attached to file in. We can sort of go through while 1, and let's get file in dot get, and let's just say C equals file in dot get, and we'll do if file in dot EOF break. So we got this while loop, and this while loop is going to go through and examine every character in the file. Right? That's the way to get at every character in the file. And remember how EOF works? It goes true when you try to read past the last byte. So the place to check for EOF is immediately after the read. So I do a get, and I check to see if the byte that I just got and put into C is actually a real byte. And if it's not, then I'm going to break. Jamie.
So, go for it. Okay, so it'll do filein.get or C equals filein.get, and it's possible that that would be the end of file, or no?
Yeah, it's possible that that'll be junk.
Okay.
Essentially, if you try to read past the end of file, C will remain unchanged. It'll just return the last byte again.
Oh. Okay.
And the only way to know that that's a problem is to look at EOF.
So it'll go to like the last byte. It'll put that last byte into C, and then it'll basically peek at the next thing with the filein.eof.
So here, let's say you're tromping along and you read the last byte, and then you go through the loop and it says, okay, I want another byte. So it goes out here and it says there's no byte there. I'm just going to give you this byte, and I'm going to say EOF is true.
Oh, okay. So then do we have to worry about C in that?
Well, you don't, because you're going to break right after that. You're not going to do anything with C.
Oh,
You're just going to break and be done.
Okay.
But let's say you didn't break. That means that C is a meaningful byte. What do you do? Yeah, so I've got this huffnode array. I can't remember what I called mine. Let me check.
And this is not huff.
Yeah. So it's called node array. What's an easy way of counting the different possible bytes?
Have the index be the ASCII code for the character.
And it's not even the ASCII code for the character. You can just do node array. Int C. It's probably not necessary. It'll probably do the cast automatically, but I'm just being safe. And if I was really being safe, I would use yeah. Okay, how do I finish this? So what is an element of the node array? It's a huff node. And what part of the huff node do I want to tweak at this point? Weight. And what do I want to do to weight? I want to add 1 to it. I can't remember what I called it. Did I call it weight? I did.
So is there some sort of like standardized way that Huffman charts are put out into the file in like the real world, such that other people's Huffman compressors will work with other people's?
No. Everybody that writes the compressor is going to write the decompressor. But you're also going to write a spec, right? Like the gzip program is all open source. Somewhere somebody probably has a specification for what the gzip header looks like.
Translated into English.
Yeah, and in fact, I know that that's the case because, gosh, it's probably been 15 years now. There's a Unix program called less. I don't know if anybody has ever heard of it. It lets you look at text files. So, you know, normally we open up our text files with VI, right, and we muck around with them. But a lot of times, or you just cat the file out to the screen. But a lot of times you want to read a text file, but you don't want to edit it, and it's also really big. And so there's this command called less, and you do less and the file name, and it lets you page through the file forward and backwards. Very simple function. Probably 15 years ago, the maintainers of the less program actually made it so that it would transparently open gzipped files. So if I do less and some text file that's gzipped, it'll automatically unzip it and then show you the contents. The reason for this is lots of manuals and lots of technical documents in Unix are simple text files, and they compress really, really well. Text files do. And so people started compressing all of these pages, and it was a pain in the butt. You had to decompress and then shove it to less. And so the less people were like, well, why don't we just sort of make that transparent for the user? And I'm assuming that at some point in adding that functionality, they had to actually go and see what the header looked like. Long story short, yes, you would write a specification. If this is going to work, make sure that you initialize the node array weights to 0. Yeah.
So then, would we, or okay, I guess in C++, if you do like if you make your array, does it automatically initialize every one of those elements with the default constructor? Okay.
There's, yeah, I mean, okay. Yes.
Oh, okay.
So if you declare this array, huffnode node array 513, it's going to run the constructor on every one of those.
Oh, okay.
Yeah. So you could put it in the huffnode constructor.
Yeah.
Which it is.
Wait. So is weight in the private part of the huffnode?
Yes. The huffnode is very simple, as you can see.
So then, but we're doing like the array element dot weight plus plus.
There's a friend class up here at the top. You see that? And that lets any object in the Huffman class have access. Yeah. I was lazy. I didn't feel like making all the. Anyway, I could have just made the whole thing public too, I suppose.
Yeah, I was gonna say, can you just do a lot of this with structs instead, like?
Yeah, huffnode could be a struct too, no question. I guess one of the nice things about making it a class is that initialization happens automatically, for example. Try to use named constants. For example, this EOL, end of list, is a -1. That's a good flag for indicating the end of list, because remember that list values are always going to be between 0 and 512. So -1 means I'm not pointing at anything, and so that's playing the role of null. So when I initialize a huff node, all of these guys, which you can kind of secretly think of as pointers, I'm initializing them all to null. In fact, I could have used null instead of EOL. Yeah.
So you're basically just using, like, when practically you would be using the L child, R child, and parent as the indices of the array. Okay.
Yeah. So when I want to set an L child, what I'm doing is just putting the index of the huff node that is the L child. The EOF ord, EOF ordinal, I'm calling 256, and that's consistent, right, with all of the other bytes. So I have all the bytes between 0 and 255, and then in slot 256 is the end of file character, EOF ORD, which I'm going to call 256. So the first new node, the first new interior node, is going to be in slot 257. So there's a quick way of doing a frequency count. Let's keep going here. The insert function.
Could you click up to the huffman header file?
Yep. Oh, Huffman. Do you want more?
Is that it? Or?
Oh, there's much more.
Oh, okay.
To be noted. Okay, thanks.
And of course, lurking in the background here in put code and put header and get header are bitstream.
Wait, put header is it? Bitstream too?
Yeah, because when I put that header out, I'm going to put out a 10-bit root node and then 9-bit interior nodes. Right, the root node could be as big as what? 12. Right, its index could be as big as 512. That doesn't fit into 9 bits, sadly.
Okay. Oh, okay.
Right.
So we're not just throwing a bunch of hits around. We're gonna.
And the interior nodes range. Sorry, not the interior nodes. Yeah, the interior nodes below root can all fit in 9 bits. So I'm going to write one 10-bit integer, a bunch of 9-bit integers, and that's going to be the tree. Because I don't actually have to write out the leaf nodes. I just have to write out the interior nodes and their children. Right? The leaf node values are going to be the children of the next up interior nodes. So I'm just going to take advantage of that fact, and not write out the leaf nodes.
Gotcha.
In fact, I can really quickly show you the bottom here. So here I encoded the file. Here it is, yes. I encoded the file with 2 lines, AB, ABC, carriage return, CCA, carriage return. And the header of this thing, if you do the Huffman tree, the root node ends up in slot 260. And then the left child is 256, the right child is 98. And then the left child, right child, you just keep writing left child, right child, all the way down. And if the left child is 256 or less, right? Like 98, 110, EOF. These are all leaf nodes, right? And we know that by their values. Okay. So that's all I have to write. And so, in fact, when we were discussing this the other day about how big the header of the compressed file is going to be, it doesn't actually have to be that big, because we don't actually store the whole 513. We just store the stuff that we used in this guy. So for this guy, I would have 10 bits here, and then 1, 2, 3, 4, 5, 6, 7, 8 times 9 is what, 72? Plus 10, 82 bits. So I'm still swamping my savings for that Mississippi example, but it's not as bad as writing out a whole 512. Yeah.
So in this case, we did write out the leaf nodes? Because we have all of the characters there, like 97, 99, those are both.
No, let me remind myself what I did here. So, point 2 here.
Oh, so when that's printed down there, it's because you get to a node and then you print.
I
this
printed
is what
out.
the children
Yeah,
are.
exactly. I printed them out. The only thing that was in the file was 260, 256. Was that a root node? I don't know. An interior node. Anyway, so yeah, we're going to talk more about this on Monday. There's a lot more to say about this program, but you have at least an idea of how it's going to go. Okay. Have a good weekend.